In Lesson 8.1, we looked at how to find the midpoint and use the distance formula in 2 dimensions. We had looked at that already in geometry. So in this video, we're going to look at how to use the midpoint and distance formula in 3 dimensions. You can derive a formula for distance in 3-dimensional space. It may seem that the formula would involve a cube root, because we're looking at 3D, but actually it involves a square root similar to the formula in 2 dimensions. Suppose x sub 1, y sub 1, z sub 1, and x sub 2, y sub 2, z sub 2 name 2 points in space. Draw a rectangular box that has opposite vertices at these points. The dimensions of the box are the absolute value of x sub 2 minus x sub 1, the absolute value of y sub 2 minus y sub 1, and the absolute value of z sub 2 minus z sub 1. As remember, distance is always positive. Let A be the length of a diagonal of the bottom of the box. By the Pythagorean theorem, A squared equals the absolute value of x sub 2 minus x sub 1 squared plus the absolute value of y sub 2 minus y sub 1 squared. To find the distance d between x sub 1, y sub 1, z sub 1, and x sub 2, y sub 2, z sub 2, apply the Pythagorean theorem to the triangle whose legs are the diagonal of the bottom of the box and a vertical edge of the box. So that little triangle there, if you can kind of visualize it, I wish we could kind of turn it to see it better, it's going to be d squared equals a squared plus z sub 1 minus z sub 2 squared. And remember, we found a squared by using x sub 2 squared minus a sub 1 squared and y sub 2 squared minus y sub 1 squared. The absolute value is kind of irrelevant since we're squaring, which they did here. And then we need to define just d instead of d squared, take the square root of the whole business. The distance d between the points with coordinates x sub 1, y sub 1, z sub 1, and x sub 2, y sub 2, z sub 2 is given by the formula. D equals difference in the x's squared plus difference in the y's squared plus, this is the new part, difference in the z's squared. Find the distance between 0 to negative 3 and 4 to 9. So we're going to plug into the formula and do the difference in the x's squared plus the difference in the y's squared plus the difference in the z's, and minus negative 3, I'm going to change that to plus 3, squared. And it really wouldn't matter what order you did them in because we're squaring anyway, the negatives would go away. And 4 minus 2 is 2 squared, 2 minus 0 is 2 squared, 9 plus 3 is 12 squared. And so we've got 4 plus 144, which equals exactly square root of 152, which would simplify to 2 square root of 38. And if you actually wanted to measure something, it'd be better to have that as a decimal approximation. And traditionally, we like to round to the hundredths place. So we got 12.33, and they didn't give us a label, so we just get to call it units. In 3 dimensions, the midpoint of the segment with coordinates x sub 1, y sub 1, z sub 1, and x sub 2, y sub 2, z sub 2 has coordinates x sub 1 plus x sub 2 divided by 2, y sub 1 plus y sub 2 divided by 2, z sub 1 plus z sub 2 divided by 2. Notice how similar this is to the midpoint formula in 2 dimensions. They ask us to find the coordinates of the midpoint of a segment with endpoints 6, negative 5, 1, and negative 2, 4, 0. So we're going to use the formula and average the x's, so 6 plus negative 2, average the y's, negative 5 plus 4, and average the z's, 1 plus 0. So we've got 4 divided by 2, negative 1 divided by 2, and 1 divided by 2. And I know what 4 divided by 2 is, otherwise I've got 2 fractions. Fractions happen, it's not that big of a deal. So instead of averaging 2 numbers, we're averaging 3 numbers. Not that big of a leap forward.